also from Johns Hopkins, who is director of the Center for Clinical Trials there, and who is the author of some of the leading books in this area. And he's going to tell us something about how these kinds of studies are actually done. Thank you.
Thank you. Is this microphone? Okay, my microphone's back. Well, I'm happy to be here, and I'm especially happy to have survived my cab ride from the train station yesterday because I had a crazy cab driver going about 80 miles an hour. And about halfway here, he cuts off a van. The van pulls alongside. The guy gets out, pounds on the door. The cab driver gets out and says, "Bring it on." The guy goes back in his van, and he goes get something out of a knapsack, puts it under his coat, and comes back out, and I'm thankful to be here and alive today. So anyway, and to satisfy myself, I actually therefore filed a complaint, and if you want to make yourself feel good, you should call NYC Taxi and file a complaint, and that will make you very happy. I mean, you listen to about 15 recorded messages and this and that and so on. Let me, before I start, let me just make a few comments on other things that have been said. I am a biostatistician by training. I live in the Department of Epidemiology, and I call myself a trialist. So, and as a trialist, what's a trialist? Well, a trialist is one who designs and conducts and analyzes and talks smart about clinical trials in the area. And you know, in that sense, I differ, I suppose, from Leon and Doug, because they are primarily concerned with causality. And in that sense, they're sort of searching, I suppose, for absolute truth. I'm searching for relative truth. I don't necessarily care how a treatment works. What I care about is whether it works. And so if it works, it works. I mean, I'd like to know how it works. Obviously, if I'm in a drug company, I'd like to know how it works because I may be able to market other drugs. But nonetheless, from the point of view of what one is trying to do, one is trying to figure out if it works, if it's safe and effective. One other comment I guess I would make with regard to questions that I've had before, if I had to give you any advice with regard to what you needed to do with regard to people you listen to and so on, and experts and so on, I'd suggest you always get an odd number of epidemiologists or biostatisticians. And one other thing I would say, I mean, and I'll probably come back to this, but at least to trialists, randomization and haphazardization is not the same. Now, if you look those two, if you look random up in the dictionary, you're going to find that it says they'll have as a synonym haphazard, but haphazard, and I think as Leon commented, is not the same as randomization, and I'll get back to that. So when you're looking at things or when you're listening to testimony or whatever, be very wary of that word random, and make certain that you know that there's a method behind that word. Otherwise, it's haphazard and not random. Okay, and one other comment I guess I would make is, you know, I've entertained myself by having written a dictionary on clinical trials, and one of the confusing words, it seems to me, in this area has to do with negative results or whatever. Well, negative can mean nil, nothing, no difference, or it can mean in the opposite direction of what you mean. So whenever you hear negative, you don't necessarily know without more detail as to whether or not the person's talking about meaning nothing or meaning in the wrong direction. Okay. Now, and I should also say that, you know, I've taught courses in clinical trials. I teach a course in clinical trials at Hopkins, and my experience there is that I've had at times more sleepers than Motel 6 has. And I know that I've been told that some of you were out in the town last night, and I have an eye for sleepers. So, I mean, they're usually gathered towards the back of the room, so I'm going to be concentrating on the back of the room primarily. So, all right, now, I was given the assignment of talking about representation and generalizability. I see the program just says those two words. I added in clinical trials because otherwise I don't know why I'm here. Now, and you know, we got to start with certain basics. You know, what's a clinical trial? Well, the context in which I'm referring to it, it's an experiment designed to assess the efficacy of a test treatment by comparing its effects with those produced using some other test or control treatment in comparable groups of human beings. And I'm sure I don't have to tell you that that word also is widely used. So, for example, when you hear in the news, clinical trials show, often that refers to the first use of treatment in human beings, and it's not that definition. It just means basically an observational study. So, not all trials are created equal, and when you're trying to assess information coming from those, you've got to know something about what the design is. Is it randomized? Is there a control group? Those sorts of things, and they play very heavily in the evaluation. And you know, there was a question before with regard to how do you protect against bias. Well, the reason why trialists pay a lot of attention to randomized clinical trials is because that's a trial in which persons are assigned to treatment by randomization, by the equivalent of a flip of a coin, by some system in which neither I, the physician, or you, the patient, knows what's going to be assigned until the coin is flipped. There's no way of anybody knowing, and that's very important with regard to the prevention of bias, because if I know what assignment is coming, or you or a patient knows what assignment is coming, they'll say, yeah, I want to enroll, or no, I don't want to enroll. So that's the primary vehicle for avoiding selection bias. And I'll come back to another aspect of selection bias in a minute or two. And as I said, that's a scientific method. That's a sacred word to the trialist. Randomization or random is a heavy currency word, and it as I said, there has to be an underlying documentable, auditable routine with regard to the way in which that's done. Otherwise, it's haphazardized. And I said that also. The primary purpose, therefore, for randomization is to remove the possibility of treatment-related bias in the assignment process. Notice the tricky way in which I said that. Treatment-related assignment bias. Again, I'm interested in relative truth. I don't care if the people coming into the study are not representative of the population in general. I am interested in creating comparable groups of people in the trial. So if I know I will have a very select study population coming into the trial. I don't care about that. What I care about is creating comparable groups of people so that from that time forward I can compare those people, and if I see a difference, I can attribute that difference to the experimental variable, namely treatment assignment. And a little terminology, I suppose. Placebo-controlled trial. Placebo-controlled trial is one where the comparison treatment is a placebo. But not all trials are placebo-controlled, and nor do they have to be placebo-controlled. In fact, if I'm testing a treatment that's already been, if there's already a proven treatment for a condition, I cannot ethically do a placebo-controlled trial. So there's only a limited set of things in which one can do a placebo-controlled trial. Also, I guess I'm reminded of the fact that people refer to clinical trials as the gold standard, and it is the gold standard. But Leon, I think, referred to this, that there's only a limited number of things you can do a randomized trial on. I mean, the studies he was talking about with regard to implants Well, you're not going to be able to randomize women to implant or not implant. Or the questions with regard to smoking and causology. You're not going to be able to randomize people to smoke or not smoke. You just can't do it. And furthermore, I often say that, you know, the things that are really important, we never submit to a trial. We just declare truth and we go on. And, you know, starting with the way we educate our kids. We say the way we educate kids is this way. We do that for 20 years, and then we discover, no, that's not right. We declare some other truth, and then we do that for another 20 years. So the important things we don't test by trials. It's just these other things. And the other terminology, single mask or single blind, double mask or double blind trial. What are those? Well, a double blind trial is one where neither the physician or patient knows the treatment they're receiving. Now, so therefore, it has to be a design in which the treatments are administered in exactly the same way. So, for example, placebo-controlled trials are double masked because the physician or patient will not know whether they're getting the placebo or the real thing. Single mask trial would be one where the physician knows what they're administering, but the patient does not. And obviously, there are a lot of trials that can be masked at all. If I'm doing a trial on lung volume reduction surgery, you're going to know whether or not you had lung reduction surgery. And there is no sham procedure for lung volume reduction surgery. So don't fall into the trap of assuming that if it's not placebo-controlled, it's not any good, or those sorts of things. The devil's in the details with regard to what is done to carry out the trial and control sources of bias. And then the experimental variable, that in the case of trials is treatment assignment. And I covered this, but just remember, all trials involve a select, non-representative study population. That's the truth. There ain't nothing, that's the fact. Why is it a fact? Well, for the simple fact that you can't study those who don't consent to begin with. I mean, you got to have informed consent. If they don't consent, you can't study them. And furthermore, there are a lot of other reasons why they're select, because if you're doing a multi-center trial and you're located in 14 cities, you didn't select those 14 cities at random. They got selected in some way or other. So that's a fact. And as I said before, therefore, as a trialist, I don't necessarily care who I study. I just want to make certain that once they're enrolled, they're treated exactly the same way and that I've got comparable treatment groups. So on this question of representativeness in trials, it's impossible to achieve. Anybody who, that's one of the universal criticisms of trials. That if I have time, I'll give you that list at the end, because that's always a criticism you can make of any trial. It's not a representative population. Duh. Yeah, right, it's not. And then those who talk about representative, well, with regard to what? Gender, age, ethnic origin, medical history, disease state, or a dozen other things. And even if you were able to make it representative with regard to one thing, you've got 100 other things that people could say it needs to be representative on. And usually when people say it's not a representative population, it means that you didn't study somebody like me. And it's irrelevant to the science of randomized trials. I don't care. Give me a trial. I don't care. Give me all women. Give me all men. Just give me a trial. Give me some information, because I can draw some inferences and conclusions from that information. And with regard to gender, well, there's been a lot of stuff on this, and I think originally I sort of got hunchwoggled into this by the combine of Berger and Gordis by suggesting I should talk about this issue, but I'm sort of tired of this issue. I had slides in here showing you what I mean, but you know, I can show them later. But the reality is that this is a gross misconception. You ask 100 people, 100 people in Sleepy, I haven't asked them yet, but I'm going back and going to do the survey, if they think that clinical trials, that women have been understudied relative to men, and 95 out of 100 are going to say yes. The only trouble is I think it's wrong. I mean, at least from studying the published literature, the truth is most trials involve both males and females. There are more female-only than male-only trials, and disease state rather than gender is the big equalizer. And meaning, if you know, as a female and a male, you may get to the heart attack ward in different routes, but once you're there and you've got the disease, you've been equalized largely. And the other truth is that gender by treatment interactions are rare. What do I mean by interaction? I mean cases where the effect is different for males than for females. And there are two kinds of those effects. One where it's just a relative difference, and the other is where for females the treatment's good and for males it's bad. The latter kind of interactions are very, very rare, and the former kind of interactions are also very rare, at least to the extent that you can find them in clinical trials. I mean, you know, maybe God knows there's a lot of things that where males and females are different, but from the point of view of what we're able to see and detect, that's a rare event. I've done thousands of tests to look for interactions, and I've found only one, and that one I don't believe. Now, validity versus generalizability. Validity, the extent to which the experimental variable, treatment, in the context I'm talking about, serves to explain the results. And the results I'm looking at are the outcomes. I mean, I do this trial, I randomize people to treatment, I treat them and follow them for a certain period of time, I observe their outcome. And their outcome, you know, if I'm trying to find out whether or not this treatment reduces mortality, the outcome I'm looking for is death. And it's actually nice to look for an outcome like that because that's a hard outcome. A lot of the other outcomes are softer, but that would be and you know, by the way, when that one occurred. So validity of the trial is the extent to which treatment assignment serves to explain the observed result in the trial. Generalizability, the extent to which it's reasonable to generalize findings to a wider population set of circumstances. And the latter is a judgment. Validity derives from the design and methods of the trial and its conduct. So when you're looking at those things, the devil's in the details with regard to what the methods and procedures were, and I would certainly pay attention to whether or not it is published. Now, I agree that publication by itself doesn't necessarily, it isn't certainly the final test, but if it's not published, I wouldn't pay a lot of attention to it. And furthermore, I guess with regard to the evaluation of these things, I've often said, you know, the results of clinical trials are definitive 30 years after they're done. So that it takes a certain period of time for stuff to percolate through the system and for those reviews and opinions to take effect. And a trial is valid if the most parsimonious explanation of the results, the treatment result, is represented by the experimental variable, treatment assignment. But what I mean by parsimonious, it means that I can explain these results with the fewest assumptions using that variable. That's what you know, simple terms, parsimony in science, at least in the context of trials, would mean. And generalizability to a broader population or set of circumstances is a matter of judgment. One's willingness to generalize depends on whether one believes that the difference represented in a broader population are likely to influence the way the treatment works. I mean, so validity versus generalizability, those are two very different things. And some basic truths, I guess. If we require representation for generalization, there would be few generalizations in medicine. I've written someplace that I said if we took out of our libraries all of those things that we left in our libraries, only those things that were based on representative populations, we have rooms for handball courts in our libraries. There wouldn't be much in the libraries because that's virtually true for all studies. And in regard to biology and treatment of disease, men and women, blacks and whites, young and old, are profoundly more alike than they are different. And it's unwise to assume that those small differences now, with regard to gender, ethnic origin, and so on, play a significant role in the way treatments work, i.e. if a treatment works, it usually works across a wide spectrum of people. And you know, when this whole controversy arose with regard to primary aspirin and prevention of heart disease, and it arose because there was a study, one of the key studies was a physician's health study that involved males only, and there arose a hue and cry that, well, we don't know anything about females. Well, of course we know a lot about females because, if it works, it works. Now, as a trialist, I was happy. I was happy because as a trialist, you know, what does a trialist do? Does trials. So therefore, there was a call for, yeah, that would help. Thank you. You a physician?
Not the kind of doctors that can help.
So what the hell was I saying? Yeah, because you didn't have to be a genius to say, well, you know, that's going to work in females. Now, you know, so fine, we'll be employed for another 10 years doing another trial involving women. Yeah, and what happened? Well, of course it worked. And I've said this, but it's a violation of the basic rules of parsimony in science to assume that the implausible serves to explain results more plausibly explained. And one of the arguments, well, one of the reasons why you randomize is so that you end up with comparable treatment groups with regard to a whole host of variables, so that you will have, at least on average, the same proportion of women as men in each treatment group, blacks and whites in each treatment group, young and old, and so on and so forth. So when I come to doing that comparison, if I find a difference, it is not due to the difference in the composition of those two treatment groups. It's due to the experimental variable. And then a couple of other primers, I suppose. You know, the basic analysis principle in trials. The initial comparison of treatment groups should include all patients assigned to the respective treatment groups should be by the original treatment assignment, regardless of what they got, and should include all recorded events for the outcome of interest. That's a basic principle. If you can't sleep at night, you read about these things, you'll discover that that goes by intention to treat or some word like that. That's what that means. And how can you tell if you're looking at a trial when the investigators aren't playing with a full deck? Well, if you see the word in the abstract or something, in this paper we're going to discuss the results of 147 evaluable patients. That almost always means you're not playing with a full deck. It means that they've thrown certain people out. They're only going to be talking about those people who had certain conditions, and they're not going to account for everybody they enrolled. Or if it says results are limited to adherent patients, that means we're only going to look at the people who took the treatment. It's sort of like that quote that you had about Galen or whatever. Well, yeah, I mean, if you're looking at only adherent patients, that doesn't tell you about the treatment. It tells you only about a subgroup of those people. Or it says analysis by treatment received, or analysis per protocol. Or they're going to say, well, we ignore the events. In this study, we're given a cholesterol-lowering drug. We know that in order for that drug to be effective, it has to be in the system for at least 2 weeks. Therefore, anybody who drops dead within the first 2 weeks, we're not going to count. We'll just ignore those. And then, you know, I wanted to leave you with my universal set of criticisms so that you have something to go home with at least. And these always work for trials. I mean, you show me a trial, I can criticize it because it's, quote, the wrong study population, as if somebody knows the right study population. the study population is not representative of the general patient population. See how that works? Wrong or inadequate diagnostic or evaluation procedure. Sample size or length of follow-up is inadequate. One thing I should mention, by the way, with regard to trials, and when you look at these, trials are good for trying to find out if something works. They're not done to find out if something is harmful. And you can't even do a trial to sort of show something is harmful. Furthermore, they're very weak with regard to adverse effects. So if there's rare adverse events, you're not necessarily going to find that in a trial. 1 in 10,000 people has this event. Clinical trial is a weak instrument for that. So the absence of bad effects doesn't necessarily mean the treatment is 100% safe. It just means that you didn't find any bad effects within the limits. And then the last one there, that the treatment differences or lack thereof can be accounted for by some unidentified subgroup of patients. Well, that's the argument that says, well, we don't know why you got this result, but I know that if we had other variables that you didn't collect, we'd find the reason for this result. Well, that's A, implausible, and B, there's no reason for me to expect a variable that I didn't look at to be distributed any differently across those two treatment groups than a variable I looked at. So it's a bogus argument. I'm out of time and out of energy.
Next question. Okay. We do have some time for questions, Dr. Martin.
That's right. Can you go back to your oh, I do here. All right.
It's the room, not you.
Can you go back to your examples of various different trials and just give
We
us,
need mechanical help.
or maybe, just give us basic examples of placebo, single mass, double mass, so we have some sense of what those look like.
Okay. Well, I referred to a trial that is en masse. That's the National Emphysema Treatment Trial. That's a trial in which people are screened and then ultimately, after consent and so on, randomized to either lung volume reduction surgery or medical treatment. So it's en masse. Patient knows what they're getting, and the physician and the surgeon obviously knows who they're operating on or not. So that's en masse. And what you have to worry, it seems to me, with regard to en masse trial is that if I know what I'm giving, will the knowledge of the treatment that I've given bias my observations? Well, again, the outcome measure there is mortality. So unless you're a scoundrel, you misreport. It's pretty robust there. A double mass trial would be a trial involving, say, a glaucoma treatment in which you're giving two patients either quote placebo drops or a glaucoma medicine treatment. Both packaged now the same way, so they look exactly the same way, so the drops look exactly the same way, so the bottles look the same way, and so on. And the patient you give the assignment as to what drops the patient is supposed to take, but it's in a mass fashion, so you say put 2 drops in your eyes morning and evening, out of bottle 14, and I, the physician, don't know what's in bottle 14. The patient doesn't know what's in bottle 14. And the outcome measure there is to observe change in intraocular pressure, and to decide whether or not to evaluate the treatment with regard to intraocular pressure. Single mass trial. Well, single mass trial are less common than either unmasked or masked. Have I done any single mass trials? at any rate, that's where you, the patient, wouldn't know, but I, the physician, would know. And why would I know? Well, because I'd have to know in order to administer this treatment. I mean, I can't mask if it causes the patient to carry increased risks. So that's the limit for masking.
In the area of clinical trials, I wonder if you could comment in regard to the strange business we've been reading about with estrogen. I presume that somewhere along the line there were clinical trials, or maybe there were not. I really don't know, but I don't understand how that whole business took place.
Yeah. Well, there, and certainly I think Leon may want to comment as well. This, of course, is an interesting story because, you know, over the years, estrogen replacement has gained great popularity because it relieves symptoms and it makes you, feel good, and it relieves symptoms of menopause and so on. And there have been certainly observational studies that give credence to that. So it's not just something that somebody dreams up. There's observational studies that support that. But as often happens, it seems to me, in medicine, the last thing you ever do is a trial, so to speak, because, they're complicated and costly and all sorts of other things. And well, we don't need a trial on this. We know it works. I mean, in my clinical judgment, it works. Well, ultimately, if you study the natural history of trials, this is a common natural history. The treatment sort of emerges. There's observational studies supporting its use. It's widely used and it's widely heralded until finally somebody says, well, gee, we really ought to do a trial. There is and was a randomized trial going on in which there were, I don't know, some 16,000 women or whatever randomized to estrogen hormone replacement therapy and control treatments, and the trial was randomized, well done, well designed, well conducted, and the data monitoring board that sees those results ultimately decided there's no evidence here that this treatment is beneficial, and in fact some evidence maybe it's even harmful, and therefore we're going to stop this trial. So that's sort of the story. Leon, you want to comment?
Well, one comment is that Kurt has given a very nice summary of that. But one of the interesting things here is that I think all the cohort and case control studies were at variance with the clinical trial finding. And there are a lot of papers being published now in the literature trying to explain why it is that the observational, by observational we mean non-randomized studies, came up with a different finding than the randomized trial did. So it's still being addressed.
Yeah.
A different finding as to efficacy or as to potential harm?
As to, primarily, I think in terms of efficacy of preventing heart disease.
Yeah, I think that's absolutely true.
Stephanie Dimitrovich, State Trial Court Judge from Erie, PA. You indicate that treatment or gender by treatment interactions are rare. How did you test that hypothesis? Because by real-life examples, that's not true.
Realize for what? I'm sorry, I didn't.
By real-life examples, our observations don't prove that.
Well, the basis for this would be looking at published trials. Now, of course, you can't look at unpublished trials, but if you look at published trials and you look for reports in those published trials of, in this case, gender differences, you don't find them. I mean, they are rare indeed. Now, as I said before, it doesn't. I mean, obviously, we're much more alike than we're different, but we're not 100% alike. And it may be possible that if I was God, I would know that some of those hormonal differences make some difference. But whatever difference it makes, it's not a big enough difference to be able to be detectable or found within the trial. Furthermore, it seems to me we want to believe. I mean, this is something we want to believe these days. We're concentrating on all the differences with regard to gender, ethnic origin, and so on. We're concentrating on I think the differences. So if it doesn't jive with the observation, it's not necessarily surprising because our observations are driven by, you know, popular perception and so on. You have to look a long time to find any interaction. And furthermore, there's an important paper that was published some years ago in which I forget all the authors, Youssef was one, in which they looked at trials that recorded a subgroup difference, and that's another word for interaction. Then they followed those things forward in time to look at other studies that were done after that to see if those differences reproduce. So it was a sort of a forward study, and if I recall correctly, not a single one, they found 17 of those, and not a single one of those reproduced. Not a single one was replicated when there was another independent study done later on.
Andre Davis from Baltimore. We encounter the term placebo effect, and I'm wondering what the real scientific take on it.
Yeah, well, we're in fact doing a study to study the placebo effect. I mean, you know, trialists, they'll do anything. You know, you got to stay off the street. I mean, usually, in the context I'm using it, almost always when I'm talking about a placebo effect, I'm talking about the effect, for example, that you observe after you've enrolled somebody into a study. So let's suppose they're randomized to placebo, and I'm doing a blood sugar lowering, you know, I'm treating diabetics. Well, and I've done this. Well, when you randomize those people, guess what happens after you randomize them? Blood sugar levels reduce in everybody, whether they're on placebo or on an oral agent. Part of that is what you call a placebo effect. It's the effect, for example, of like having been enrolled in a trial and say, gee, I better watch my diet. I mean, you know, this is not good stuff. But the way you deal with that in a randomized trial is you talk about the difference. You look at the difference between the blood sugar level after 1 year of treatment in the trial in the placebo-treated group versus those on the active oral agent. You subtract that out. So you're always talking about a difference. You're talking about the difference of treatment effect. But there are people who believe placebo has a therapeutic effect in and of itself. And I don't know about that. I have said that of all the trials I've done, and I've done a lot of them, guess what's the best treatment to have been on? You guessed it. Nothing. Now, what does that tell you? I mean, that should tell you one of two things. Either I'm a bad judge of people I work with regard to the way these treatments get selected, or we are using a lot of treatments that are ineffective, useless, and harmful. And I guess maybe you could tell what my bias is. So but until you've done a trial, you're faced sort of with the situation you're talking with regard to hormone replacement. I'm sure I haven't answered your question, but I didn't sort of spend enough time on it.
I wanted to ask a question, which is, yesterday, I know you weren't here, our toxicologists were talking a bit about genetic factors. And I wondered to what extent there were now problems, because if genetics plays a role, you do not yet know that this gene plays a role, how do you handle randomization in light of that uncertainty?
Same way. Well, look, if you think you have an important variable, if you believe that gender is an important variable, and it's more than just what we think about it, if we believe, we have evidence, prior evidence going in that we think that the treatment effect is going to be different in males than females, then I'm going to, quote, control for that in the randomization. I'm going to make certain that my groups are balanced with regard to gender. But if I don't have that, I'm not going to do that, because that complicates the randomization. My answer would be the same to you with regard to gender. Genetics. If I believe that this is an important variable, then I would randomize it. But I'm sure I don't have to tell people in this audience that you get any learned group of people together, and they'll come up with a hypothesis for anything, even, you know, I mean, an explanation, even if it's not, I mean, just give a clinician a set of data, and they'll give you a hypothesis as to the mechanism by which it works. It just turns out it's wrong a lot of times.
Thank you. Okay, our next speaker is Stephen Stellman, who was not on our original program and to whom we owe a debt of gratitude. When the original speaker, who was going to speak about the breast cancer study on Long Island, withdrew last week, she suggested that Professor Stellman would be a wonderful substitute, and he very graciously agreed to fill it. So he is a professor of epidemiology at Columbia University. You have his bio in the additional materials that were in that black folder you were given when you registered. And again, we want to thank him very much.
Thank you. And it occurs to me that the last time my wife and I were in a legal environment with someone named Gordis, it was 35 years ago under the chuppah, and we were signing the marriage contract with Leon's father. I've known him for a long time. And I'm pleased and honored to be here, and I'm always happy to fill in for my longtime colleague Marilee Gammon, who's now at the University of North Carolina. We're still collaborating on this study, and may go on for some time, as studies generally do. And I was struggling a little to find out why I'm really here, but I guess you were interested in hearing some real data for a change. And so this will constitute somewhat of a report from the field, and possibly some of your next cases in the making. Breast cancer is, unfortunately, a very common cancer. It's a very serious disease. Where are my... and it is caused by many different things, some of which are well established from the panel on the left, but all of those, if you look at them carefully, are things, except for ionizing radiation and alcohol consumption that we've heard quite a bit about today. Many of these are what we call host factors. They're characteristics of a person, and many of them, even though they are, in some sense, environmental, they're not things that we can change very easily. The ones on the right panel are being studied very actively now, and you've heard a little bit about some of those. But the concept here is that many of these are widespread exposures. They're things that many people are exposed to, and we don't really know much about their relationship to breast cancer. And interestingly, the motivation for doing the studies that I'm going to describe has not come from astute clinical observations, as many of our epidemiologic studies do, but they really come from the field, from the grassroots, from advocacy organizations who are well organized both socially and politically. And to me, actually, that's been a good thing. We have developed a mutual respect for each other, and I report to several of these groups frequently about our findings, and they grill me and my colleagues mercilessly sometimes about whether things that they necessarily do or don't believe. And we've developed a kind of a symbiotic relationship about how their concerns affect our practice of epidemiology. Why Long Island? Well, Long Island really does have higher breast cancer rates than the rest of New York State as well as the rest of the United States. And it's true both in new cases, and it's true for mortality. And why the things that we're studying, particularly, I'm going to talk about a couple of broad classes of chemical compounds that are widespread environmentally. This is from, if you can't see, from Jones Beach, very popular Long Island beach in 1945. And the fogger was out. It came around several times a day, and many people remembered it. And one of our patients produced this photo. And I remember as a child in Columbus, Ohio, chasing mosquito foggers around in the 1950s. So this is something that pretty much everybody has been exposed to. There's another chemically related class of chemicals that really has nothing to do with pesticides, but has similar chemical and biological effects, and those are called PCBs, polychlorinated biphenyls. What they have in common with the organochlorine pesticides is not only that they have similar chemical structures, but they have similar biological effects, and one of those effects is estrogenicity. That is, they behave in certain situations very similar to the way that a woman's natural estrogen behave, and we already have known for many decades that estrogen is a major factor in development of breast cancer. However, there's already we see a few seeds of dissent here, and some cracks in a not too well constructed scientific theory right from the start. Not all PCBs are estrogenic. In fact, some of them are anti-estrogenic. They have exactly the opposite properties in biological system. And then there's a third class over on the far right column that's neither estrogenic nor anti-estrogenic, but they're a group of compounds that induce or get some of your enzyme systems working rather in a similar way that many carcinogens do.
What do the numbers in the table mean?
Oh, I'm sorry. The numbers, there are, PCBs is plural. PCBs is a group of many chemicals that are all similar but not entirely identical, and they differ in the number and the positioning of chlorine atoms around a pair of six-membered carbon rings. And there are exactly 209 of them, geometrically possible. About 100 or so of them occur in the PCB formulations that have been released into the environment and that were used industrially for many years under the trade name of Aerochlor. And they all have numbers. They're numbered from 1 to 209. And the ones in the columns there are their numbers according to a standard international scheme. The numbers don't mean anything to people who don't study these, but for people who study these for any length of time, they get to be very familiar. For example, in the far right-hand column, number 153 happens to be the PCB that is the most broadly distributed in the environment, and it makes up about 25% of all the PCBs that you'll encounter in the environment and in your body. Another concern about these chemicals is not merely are they widespread and that we're constantly exposed to them, but they hang around in our bodies for a long period of time. They are lipophilic, meaning that they are attracted to lipid stores or fatty tissue stores in the body, where they go and they just stay there, and those stores become a reservoir, which then over the years, even long after your exposure stops, they leach out back into your bloodstream, and they tend to congregate in the lipid portion of the blood. So you will commonly see reports of analyses of PCBs or DDT as lipid adjusted, which means that the concentration in the lipid part of the blood is usually measured. What you see in the few numbers in this table are called half-lives. This is the amount of time in years that it takes for half of the amount of stuff in your body to decay or disappear. So, for example, for DDE, which is the main breakdown product of DDT, because DDT disappears pretty quickly, but your body breaks it into DDE, and it also becomes DDE in the environment. DDE has a half-life of 7 years. That means that if you had a certain amount of your body at the age of 50, by the time you were age 57, you would still have half of that amount left in your body. And by the time you were age 64, you would have a quarter of the original amount, and on and on and on, and it would never really go away completely. And I sneaked in a line at the bottom here. This last line, TCDD or dioxin, is not a PCB, it's not a pesticide, but it is structurally related to the PCBs. It generally occurs in the environment from the similar pollution sources as PCBs, and it is a compound that has caused us a great deal of legal as well as medical concern, and you'll hear a little bit more about it later. Now, as often happens in epidemiologic world, we had a flurry of fairly small, I won't say fairly small, very small study from an epidemiologic viewpoint that showed a positive association between the amount of organochlorine compounds in people's bodies and the risk of breast cancer. And at first glance, this might seem to be somewhat meet the test of consistency, but they're not terribly consistent. The findings were, some found an association for some compounds, like the one in the top, beta-hexachlorocyclohexane, which is a common pesticide. But that study didn't find DDE or DDT or PCBs. Others found DDE, but not PCBs. And the last study, which was done at the Kaiser Permanente group in California, was found DDE dose response in whites and blacks, but not in Asians. And so there's inconsistent evidence from fairly small studies, but this is enough to leverage epidemiologists into writing grant proposals and concern citizens into believing that there is enough of a probable cause to do some more rigorous studies. And so, as a result of the let's say, political organizing, this is really one of, there are many epidemiologic studies that have been triggered by legislation, but as far as I know, this is the first and only piece of legislation with these rather peculiar properties. You don't see it here, but the law actually specified the design of the study that would be used, the populations that it would be used, that would be studied, and then it listed these 6 sets of hypotheses. So there was very little left to the discretion of the epidemiologists. So I call this mandated epidemiology, and it has some interesting consequences. Oh, you said this little thing that slipped in at the bottom there is someone was talking about the wish bias. This is an example of be careful what you wish for because you might get it. At a certain time during the legislative process, when the law was still being put together, it was decided that it was great to study Long Island, but there were other hotspots in the Northeast United States too, and therefore someone wrote into the legislation that we should study the 2 counties in northeastern United States that had the highest mortality rate from breast cancer. And so one of those is Schoharie County, which is just to the southwest of Albany. The other is Paulding County, which is in upstate Connecticut. Trouble with Schoharie County is that while it had the highest mortality rate the year the legislation was proposed, the following year it had the lowest rate. And the reason is very simple. It is one of the least populated counties in all of New York State. And all we're dealing with is background noise. And one year they had 5 cases, the next year they had 2 cases, and that was enough to bring it from the top to the bottom. We have done a small study there, and we essentially find nothing different than in the larger study, which you'll hear about momentarily. The result, the law itself was a legislative function, and the executive branch's response was to direct the National Cancer Institute to create a small office in one of its internal branches and create an entity called the Long Island Breast Cancer Study Project. And this is a piece of their website. It's still on the web, and you can see it. And the Long Island Breast Cancer Study Project actually was an umbrella for somewhere between 8 and 12 individual independent studies, although 1 or 2 of them cooperated with each other in some way. And 2 of them, the 2 on the top, American Health Foundation, which is now called Institute for Cancer Prevention, which is on the Danner slide. That's one of the 2 studies. And the Columbia University Case Control Study, which Dr. Gammon was and still is the principal investigator of, is the other of the 2 large-scale case control studies that were done on Long Island. The remainder of these studies most of them are still going on, and they're directed at somewhat different aspects of the hypothesis, so I'm not going to have time to talk about those. Well, our 2 studies, the American Health Foundation study, which I ran, and the Columbia University study, which Dr. Gammon ran, but which I'm also a part of, they're the same and they're different. And I'm not sure whether they're more the same or they're more different. You've heard from Dr. Gordis the broad outlines of case control studies, but there's an immense amount of nuancing. And our studies were different to the extent that our study was done in the 2 largest hospitals in Long Island. We only used patients from those hospitals. And Dr. Gammon's study tried to enroll every woman who developed breast cancer over a period of 1 year. And there are a number of other differences. The Columbia study is about 6 times the size of the American Health Foundation study. But by and large, we had compatible, similar aims. And also, we were in the field at different periods of time, so there's actually no overlap in the study, even though they're done in the same geographical area. There are, as I said, nuances to case control studies, and it's like an onion that you can peel off one layer and get down deeper and deeper. And so we were in 2 hospitals. We had over 200 cases and 300 controls, but the cases themselves were of several kinds. There were almost 200 women with invasive breast cancer and another 33 with carcinoma in situ, which it's still unclear to us whether there is an etiological or whether it should be lumped in with the invasive cases or not. So we analyzed them one way and then we analyzed them the other way. Our controls were women with benign breast disease and a number of women with surgical conditions where we would expect them to ordinarily have waste fatty tissue that the surgeon would just throw out. And we dutifully went into the operating room and collected the waste tissue and sent it to our laboratory and analyzed it. All right, well, this is a little too busy for life, and unfortunately the bold facing that I want to draw attention to is not very clear. There's lots of different ways to compare these different compounds against each other. And one of the ways we do it is by fingerprinting the PCBs. We looked at 14 of the 209 different PCBs, and I simply ranked them by how much they contribute to the total fat or the total serum that we draw. And we, just out of interest, we compared it with the literature on other animals and other human studies. And if I look over here, my study, the American Health Foundation study, is shown in these last 2 columns. And our fingerprint profile is very similar to the profiles of fish, aquatic birds, aquatic mammals, and another study of human fat. But it's very different from one particular human study that was done by Mary Wolfe at Mount Sinai, who was a longtime collaborator of Erving Selikoff. And the reason that her study, she found a high percentage of these very lightweight PCBs, and we found a high percentage of the middleweight PCBs. The reason her study is different from everybody else's was because she was looking at an occupational group who manufactured the PCB capacitors. And those people were exposed very heavily day in and day out. And when they drew the blood and the fat to analyze from these people, those people had been exposed heavily during the same week. And so these very light ones generally disappear over time. So what that tells us, I think, is that our group and the environmental groups are exposed. We think our people are exposed environmentally and obviously not occupationally. We can do, this is a fingerprint between the cases in this column and the controls in this column. And the fact that the numbers are pretty much identical means that the cases and the controls are pretty much alike in the percent distribution of their PCBs. And we've done many other statistical tests which have been published already that indicate to us, using the same criteria using the methods that Dr. Gordis explained and the criteria that Dr. Weed discussed, we detected DDE and PCBs in everyone, every single woman that we examined. And there are hundreds and hundreds that I haven't reported on in this talk. We detected some amount of these chemicals, so everybody has them, and I presume that means you and I. But the concentrations, sometimes the phrase we use is a body burden. The amount that people had in their body that we could measure, whether it's DDE, which is the common form of, I gotta go back.
Use the wheel.
Substance, our study is negative in the sense that we show no association in a fairly large group of women. A fairly large was about, as I said, about 230 cases and about 300 and some controls. That's the American Health Foundation study. The Columbia study, in the same part of Long Island, but done a year later, and on 6 times as many women, and had a much wider net to cast in epidemiologic terms. We sent people into the women's homes. They conducted a face-to-face questionnaire that lasted, an interview that lasted about 2 hours and covered many different aspects of people's lives, including their reproductive history, where they had lived, their occupations, things that they had used that might have been toxic, alcohol use, and on and on. We drew two or three tubes of blood from them. We took some urine. We left behind a questionnaire because of the time constraint. We left behind a questionnaire that they filled out at their leisure about their usual diet. And we got consent for release of medical records. We also did something that is very rarely done, but it's becoming more common and more interesting, and gives us this study an extra dimension that we don't often see in epidemiologic studies, and that is we did environmental sampling. We went into their homes. We drew 8 tubes of water from their tap, with different types of preservative to test for different kinds of environmental chemicals. And those were all analyzed by the Suffolk County Water Bureau. We went into their yards and with an auger. You know what an auger is? It's about a 1.5 long steel hollow tube with a crossbar at the top. And you just jam it down into the ground and twist it, and it comes up and it pulls up a certain amount of soil. And we sent them to our labs at American Health Foundation for analysis. And we went into their homes with a kind of a super duper vacuum cleaner that was developed by Battelle Labs in Columbus, which has a carefully calibrated flow rate. And we had a little special protocol where we taped off certain areas of their rugs and vacuumed up their dust and collected them in an Algene bottle that then was sent to a laboratory in Texas for analysis. And so from those assays, we're still carrying out some of these studies now. We're looking at the environmental concentration of many different types of things, including the pesticides that we studied, and the PCBs, and a number of common or non-common contaminants of water. So those studies are still in progress, and it's going to take some time to make sense of all of this data. But we've already completed and published sort of the main hypothesis of the study, which was to look at 2 kinds of things in their blood. One was a type of DNA damage that's caused by PAHs, or polycyclic aromatic hydrocarbons. This is really one of the most common pollutants that people are exposed to. It comes from automobile exhaust. It comes from many types of food preparation. And we found that there was a slightly elevated risk, say 1.51, for people who had the highest level of these adducts, or evidence of DNA change, but there wasn't a dose response. And in fact, this is very, very similar pattern to a completely unrelated study, but except for the fact that it appeared on one of Dr. Weed's slides, from one of his alcohol studies, way back, about 15 or so years ago, that Larry Garfinkel and I did at the American Cancer Society. We found exactly the same pattern, where we found a relative risk of 1.5 for women who had drunk a very large amount of alcohol regularly, and no increased risk for women with moderate or reduced levels of alcohol. So I'm not sure what to make of this, and I'm going to leave the interpretation to the people who know how to interpret this. The adduct levels, trigger here, were not associated with smoking and not associated with food intake, so we don't know where these PAHs are coming from, except probably from automobile exhaust. We looked at their organochlorines, just as in the American Health Foundation study I described, and the odds ratios or relative risks, none of them were significantly different from a relative risk of 1, which means no association. DDE was only 1.20. Chloridane, which is a very common termite-killing compound that was used for many years on Long Island, had a relative risk that was almost identically equal to 1. Dieldrin, which is also a common but now no longer used insecticide, is 1.4. And PCBs also had no increased risk. So 2 studies done, well, they have the same superficial design. They're done rather differently in their design, in the details of their design. And what do we find out? Well, first of all, I'll mention this again because this is really kind of distressing. All women, and I think I'm comfortable generalizing to everyone, has measurable levels of these compounds in their fat and blood. These compounds are not benign. They include carcinogens. These are, it's not my opinion. The carcinogenicity is based on the judgments of many official as well as unofficial agencies. International Agency for Research on Cancer in Lyon, which is one of the premier evaluating agencies for human carcinogens, the EPA and other agencies. They include carcinogens, they include compounds that are endocrine disruptors, that is, that they interfere with the endocrine metabolism process, and so presumably, and that's all I can say is presumably, they could affect risk of breast cancer. But we found no association between the levels of these compounds and the risk of breast cancer. Well, we like to go a little bit deeper and ask, why can any epidemiologic study be negative? Well, first and most obviously reason is they really don't cause breast cancer, period. And it has taken a lot of time for some of the more, say, committed activists to accept this as a possibility, even though it's impossible to prove the negative, but it is a major possibility. But epidemiologists have a very strong tradition of coming to the end of a presentation and shooting ourselves in the foot, and here's where I do that. And here's all the reasons we could be completely mistaken. One, the size of the study is too small. There aren't enough cases and weren't enough controls. If we only had more people, then those slightly increased risks that weren't statistically significant would be significant. That's a possibility. Number two, which may be more plausible, is the exposures really, yes, everybody's exposed, but they weren't exposed to enough. There are areas of the world today, like Mexico, where DDT is still the insecticide of choice for malaria control. And people there, particularly who spray DDT, as well as the people who live and work in the fields where it's sprayed, are constantly exposed. And maybe that's a higher risk population. We haven't really looked well at multiple exposures. That as several of our speakers said, people are exposed to more than one thing. And we try to control for as many things as we can think of, but we can't measure everything in the environment, and we may have overlooked something. But my sneaky last point that jumps me into the conclusion is that maybe we really haven't assessed our exposure very well. After all, as Dr. Gordas pointed out, in epidemiology, you only got two things. You've got an outcome, that's the disease, and you've got an exposure. And if you don't take care of the exposure very well, you've got nothing. Breast cancer takes many years to develop, like every other cancer. The chemicals accumulate in our bodies over a lifetime. Our bodies also know what to do with these chemicals. We metabolize them, we excrete them. Even though they stay in our bodies, if we're not exposed to any more, gradually the levels decrease. And I showed you some numbers near the beginning to show us how long it takes to get rid of them. So I come in, now I'm going to get to Dr. Weed's issue of temporality. And this is a major blind spot in practically all of the studies of breast cancer and environment. And that is that I come in to your house, or you come into my hospital, and I take a tube of your blood, I send it to my lab, and say you've got so many nanograms of DDT. That's just what you've got today. From that, I'm inferring backwards to your entire lifetime's worth of exposure. And the Institute of Medicine has elegantly pointed out in a monograph on Agent Orange, not on breast cancer, that people who have low levels today, there's several possibilities. They could have been high long ago and now they just decay. Or they could have been low long ago and they're still low. And to tell you the truth, we can't tell the difference, and we don't know how to tell the difference just from that one blood sample. So, newer methods are in the works, and they are, there's rapid technological development going on, and there's several new things that are very exciting. The geographic information systems, which I'm sure you will hear more and more about as time goes on. The Silent Spring Institute is doing a similar study to the Long Island study out on Cape Cod. And they built a very elaborate geographic information system that goes back 30 or 40 years and incorporates data on water quality that's been measured all of those years in practically in every one of the 130 water supplies on Cape Cod. And there are some other systems here I'll go past. We've also measured BAP, benzoate pyrene, in the soil, mentioned that before, and just to show you that we're not ready to publish these results yet because we can't relate this to breast cancer risk, but we do find that the farther we get out from New York City, the less there is in the soil. And that probably reflects the traffic patterns. We're working with a traffic pattern expert. What I tell people, because they're, breast cancer advocates and ordinary citizens don't want to, they just have you stand up here and say, here's the end of your study, now what do we do? Well, we have two legalistic and two really social and technological things that we recommend right now. One is, you may consider this apple pie, but we really should enforce existing laws that we have on toxic chemicals. I can stand and pontificate on that, but many of these laws are really badly enforced, if at all. Remediation of existing environmental problem areas, such as Superfund sites, which are already in big trouble. And we recommend monitoring the use and exposure to suspect chemicals in high-risk population. And I'm going to conclude with one little thing here, that because Judge Jack Weinstein is here, and we've drawn so much support from him over the years. There isn't an obvious connection between this breast cancer and pesticides and Agent Orange, or is there? Well, you saw this picture once. Well, it doesn't look a whole lot different from what we did in Vietnam. Here is the legislation that enabled the breast cancer studies. And here is the legislation that has directed the Veterans Affairs to set going 10 years ago a wheel of events that has resulted in Gene and I having a contract from the National Academy of Sciences to develop some of these new technological areas and methodologies into exposure assessment tools. And so based on data that have been around for a long time, but which Gene has really spent an enormous amount of effort making scientifically useful, we can track the flight patterns of over 9,000 individual Agent Orange ranch hand missions in Vietnam. We can tell exactly within geographical precision or cartographic precision where they are, thanks to the data that Judge Weinstein helped preserve and which we've been building on. We know where many of the troops are, and we hope not too long to be able to tell with a good deal of certainty where the great majority of our troops were in Vietnam. We've gone back 40 years or more to an old hand-drawn soil map of Vietnam and brought it into the computerized age and mapped out the soil regions because dioxin decays in different types of soil at different rates. And we've developed a geographic information system of our own, which was just published this month in Environmental Health Perspectives, that allows us to take information on where military units were, or where the hamlets or the people of Vietnam were, tie them to the different spray histories, and produce measures of exposure that we are now planning to use in studies of the health effects of our own Vietnam veterans. And that's my talk. Thank you very much.
That was such a provocative talk. We really had no time for questions for Dr. Stillman, but I think we should have one or two. So if anybody has a question to ask, please. All right. And if not, as I said, when Dr. Stillman graciously agreed to fill in for Dr. Gammon, he suggested to me that perhaps the person we really ought to have on the program was his wife, Jean Stillman. And when I spoke to both of them, I decided that the best of all possible worlds would be to have both of them on the program. So I am extremely grateful to her as well for agreeing on this very short notice to be part of this program. She is professor and deputy head of the Department of Health Policy and Management at the Mailman School of Public Health at Columbia University, and she's going to speak to us about some of the limitations of epidemiology, And then I'm going to ask all the panelists of this morning to please come up here to have some discussion that tries to relate together some of what we heard yesterday, some of what we have heard today, together with other questions that you may have and that the panelists may have for each other.
Thank you very, very much. This is going to be a first in 35 years where Steve's going to have done virtually all the talking and I'm going to say very little. So, I am actually not an epidemiologist. I'm just a poor physical chemist who's been muddling around in public health for some time. And I just thought that I'm going to give a very, very short presentation and to really bring up the other side of the consideration of the use of epidemiology in the courts and in public policy, and that is, what are the questions that we can't answer? You've heard some absolutely wonderful presentations, classical presentations on what you can learn from epidemiology, but in terms of what use do you want to make of it in the court, and what are the issues of fairness? I think that there are some very unfair things that are associated with epidemiology, and that is because of the nature of the natural experiment that most epidemiology is built on, and the nature of what we as a society decide to pursue and what we as a society decide to study. We heard a lot, and the essence of much of the presentation is to be able to tell whether or not one has achieved an effect. Is there a significant difference between a case and a control? But there are four really basic elements of an epidemiology study. One is, yes, the statistical significance. How sure are we that what we've observed is different from what we would observe from the natural variation of human beings? What are the odds that you have that what the effect that you've observed is not one that could have occurred by chance? And that's the statistical significance. Is what I'm seeing real, or is it a chance occurrence? This is going to be directly a function of how big the study sample is. The shoot yourself in the foot list at the end of Steve's presentation are the problems. How big is your sample, and how big is the effect? If asbestos was a much weaker carcinogen and didn't have the synergistic effects that it has with cigarette smoking, we would still be blowing asbestos over all the pipes and buildings because we wouldn't have observed the effect. It also helped that it caused an extremely rare tumor. The fourth thing is statistical power, and which addresses the issue of what are the odds that you can actually observe an effect. Okay, that you're not making an error and missing an effect that's not there, that is there. It's a different concept from determining whether or not what you've occurred could have occurred by chance. You're addressing the power, the question of, can my experiment find an effect that's there? And that's why you want larger samples, and that's why you want higher effect size. Knowing any three of these factors automatically determines the value of the fourth. And if you want to be 99% sure, you're going to have a lower power. If you want to settle for being 80% sure, then your power to observe an effect increases dramatically, but you're a lot less sure that what you're observing is real and not random. That's when you begin to think about the social implications and the fairness of all of this. And I just, in the 1 day's notice I had, and last night I had to redo a doctoral student's entire, that's why we have no PowerPoint, I had to redo her entire set of calculations so she could finally graduate. So I'm going to just talk the old-fashioned way. And I just listed just a small handful of factors that have an effect on whether or not you have the power to observe an effect, and whether or not the study is actually going to be done. And I've thought a lot about this since we undertook the Agent Orange work for Judge Weinstein some decade ago, I guess, by now, because there we had a situation where exposure was absolutely not easily dealt with, and where there were just a handful of animal effects and nothing that was worth its salt in terms of human effects. And you have to ask yourself, why? We dropped 20 million gallons of herbicide in Vietnam. We had a very complete record. I just spent the last year redoing that record, and it's going to be published very soon in Nature. We found more, but we had 20 million gallons. We had a whole file. We had 3 million troops. So we had all the things that one could have, but we didn't have the social will to do the study. And in fact, there was a counter will in which studies that were well underway by the Centers for Disease Control were completely abandoned in 1989 for what was later felt to be political reasons in congressional investigations. Why is this? And I just made a quick public health list of why it is. People who are exposed to weaker agents, things that don't have sexy effects, are less likely to be able to have epidemiological evidence to get to corroborate their claims. Number one, it's going to be very hard to get people to be interested in doing the study. Doing an epidemiology study is incredibly difficult to begin with, and it's very, very hard to convince someone to do a study on a weak effect, because it's likely going to be a very nebulous finding unless you can garner enormous amounts of data from a lot of people, and you're not going to be able to get anybody to pay for such a study. And I think that's what Dr. Gordis referred to as one of the ways in asking, well, can this study be done? The other question is, will this study be done? The other thing that's incredibly important is that people who are exposed to weaker agents are less likely to actually develop the disease, develop the symptoms. It may take a much longer time for the dose to have an effect. And if you look at a list of what are the agents that we actually know something about, by and large, these are, to a very large extent, these are agents that alert practitioners, like the cataracts. I forget who talked about the cataracts that wasn't an epidemiologist who caught the cataracts, it was a clinician. Mesothelioma, the vinyl chloride by the alert practitioner in North Carolina or Kentucky. Mesothelioma. These are all signal tumors that are caught because of alert practitioners, or else, like in Building 6 in Roman Haas, you had 4 young guys all getting lung cancer from an incredibly potent alkylating agent, and it was picked up, it was observed. So that the role of the alert practitioner and the role of people talking to each other has had a very large impact on whether or not a study gets done. People who are exposed to, small numbers of people who are exposed to something are just never going to have their day in court, because by and large you're never going to be able to do an epidemiological study on them. They will not have had sufficient numbers of people to be exposed to something for a sufficiently long time to be able to have the power to detect an effect. This is an issue of fairness. I think of, if I were a chemist or a chemical engineer working for DuPont, which happens to have a very excellent system for screening out which chemicals it goes forward with in production. So I'm in the pilot plant, I work with something, I get exposed through an accident, I have 20 coworkers. DuPont then goes through its whole series of tests, which are by and large in animal studies and toxicology studies, decides to abandon the production as possibly too risky and not wanting to have lawsuits and class actions 20 years down the pike. Well, what are those people, those 25 people who've been exposed, are never going to have any evidence other than animal and toxicological evidence to back up their case. Does that mean that epidemiology wouldn't be a good thing? Of course it would be a good thing. but I doubt that it would ever take place. So we have a representation fairness issue. I hate to use words like representation and fairness in front of judges because I'm never quite sure that I'm not using some kind of reserved term, but I just mean it in plain English. I think that we have to understand the abysmal state of medical record keeping and the fragmented healthcare delivery system and all the impediments that exist to trying to gather epidemiological data. One of the papers we're writing for our NAS study is a paper that I'm calling Missing After Action. We tried to find 12,000 American legionnaires that we found, most of them, that we had looked at in 1984. The Defense Manpower Data Center could only give us 700 Social Security numbers out of 12,000 people. They got a supplement of $20 million a few years ago to upgrade their manpower record system. 700 out of 12,000. Luckily, the credit card people are much better at keeping track of people than our own government is. Extracting military records, 16 to 20% error rate when you pay them to have their own clerks extract. 20% of the records are missing. Clerks at the National Personal Records Center, for example, are not given telephones because in 1950 it was decided that the new invention of the telephone would distract the clerks, and they haven't gotten around to amending that policy yet. The NPRC is run by the National Archives. Anybody who's done a real-life hands-on epidemiology study knows the extraordinary difficulty of finding people, accessing records, and now with all the new human subject regulations, it's not clear what other roadblocks are going to be in the way. There are social disparities about who gets studied. HIV gay activists, Long Island breast cancer women who are politically well-connected, they can spur a study forward. People who are in the less fortunate groups cannot. In general, we have not done a good job of measuring hazardous exposures, and without the exposure, you can't do epidemiology. And monitoring, record keeping, consolidating those records are pivotally important to this. I'm not going to spend much more time except to make the suggestion that there are two things that are wrong with this kind of session. Number one is that for judges, I think it's a mistake to separate toxicologists and epidemiologists, and that kind of information and that kind of approach has to be integrated. If you look at the work of the International Agency in Research of Cancer, National Academy of Sciences, Institute of Medicine, any of the agencies charged with interpreting science, they will look at clinical data, they will look at trial data, they will look at environmental data, they will look at toxicological data, and try to their best ability to integrate it. Second problem is, I'm never an expert witness. It's just a role that I can't come to at all. And the problem is that it should be the judges that are up here talking to a room full of people who are doing the research out there and telling us what you need and helping to set up the hierarchy and helping to set up the list so that the list of reviews that Doug Weed showed, which is perfect for the NCI's review policies, is not wholly applicable at all to the needs that you have. And it seems to me that this is backwards, and that the legal system has to say, these are the policy criteria, and these are the needs, and how can you develop the working rules to meet these needs? Because you're never going to be able to get an honest researcher to be able to look at epidemiology or even animal studies and say, I am 100% sure that this is where it came from. But if we could develop criteria by which to say, this is my Chinese menu of choices and options, and take the flow chart that Dr. Gordis had and see what the options are along the way, then you can begin to have a more functioning, reasonable system than I think we do right now. Thank you very much.
Okay, I'd like to ask all of the panelists who we heard from this morning to come up here. We've heard a lot of very profound provocative questions from the judges. I'd like to give the panelists an opportunity to react to each other a little. And I also have some questions that I would like to ask them, if no one else will. But first, I'd like to give all of them a chance in light of some very different things we've heard from them as to anything that they would like to talk about further. Anyone? Liam.
Gina, I enjoyed your talk. What do you propose?
Well, I think what I would propose is that we have to take a very careful look at the choice boxes that let's say DuPont uses for deciding whether to go ahead with production. They very carefully thought of what are the in vitro tests, what are the in vivo tests, what are the small animal assays that are important indicators. I think we have to look at things like structure-activity relationships and see. Because ultimately, our burden of proof is not that, I don't think that we want to be 95% sure about everything. We want to, I mean, I don't know what your levels of proof are. The one time I was on the jury, I had some guy who was a murderer. That was one level, but the level of certainty has to be one that's assigned by society. It is not a scientific problem, and it is not an epidemiologist problem. It's a policy social problem, and then we can deal with it.
Well,
that's a good
okay, actually, in the back of your briefing book, one of the things that we included was a transcript of a session that was held at the National Academies of Science at the request of ALI, which in writing comments for its new restatement of torts included something on proving causation in toxic tort cases. And the remarks were remarks that the reporter's notes were objected to largely by plaintiffs' groups, but by other groups as well, including some scientists. And this was really, ALI simply asked the Academy if it could produce a number of people to discuss with the reporters how scientists go about making these kinds of decisions. Doug Weed was on that panel, so was Leon Gordis, and there were a number of other people. I think it's a very interesting but difficult transcript to read. But one of the questions that came up there, which perhaps relates to what Jean just said, was the suggestion by one of the people, not Doug or Leon, that epidemiologists are really never asked to answer the questions that would be the most useful to the legal profession, which is not just is this sufficient, is this evidence sufficient to prove causation, the epidemiological studies that you have investigated, but are these studies sufficient to be suggestive of causation? And that would be a question that would track much better with the preponderance of the evidence standard. And that in addition, they should be asked about, is this evidence really insufficient to prove causation, which is also not quite the same question as to whether it is suggestive or whether it is sufficient. And finally, the fourth question, but one which many epidemiologists think that there is no answer to, is whether one can say that this shows that there is no causation actually proving that. Now, do you think, I mean, one of the things that emerged at that discussion was that the epidemiologist felt very uncomfortable with making such a judgment about something being suggestive. Tracks somewhat with Doug's study about at what point in time did one decide that maybe different kinds of cancer could be caused by smoking. I mean, at what point did that sort of creep in and why?
Is it on? Is this on? Okay,
Yes.
good, sorry. Yeah, I think the questions that you just asked are really interesting ones. To sort of substitute sort of 4 questions for one. It's not whether it's causal or not, or we're sure it's causal, with whether it's suggestive of causation, and then another one might be sort of whether we don't really think so, but we're not really sure, we can say no, and then the other one would be no. Well, I mean, in a sense, that's exactly what we do now. We don't have those labels on it. Sometimes we say, yes, we are convinced this is causal. And other times we say, there's nothing there for us to say it's causal. And then there's this stuff in between. Now, you can call it suggestive. Whatever you want to call it doesn't really matter. The question I really would like to know is, how would we know if we made a statement like that we're right? That suggestive means something. And we don't have a way to do that right now. And the only way I can think to figure this thing out is, as I mentioned, is to go back into the past. And I think you guys would be as interested in our answers as we would be. And look at situations in which we indeed have decided, and there is a consensus in the scientific community, in the policy community, in the legal community. Everyone says, yes, in fact, this thing causes disease. We know this. So if we went back into that history and said, okay, at what point did we make that decision in the scientific community, and how much evidence existed at that time? That is the beginning of a technique for what I'll call validating this methodology. Now, I wish, and after hearing Kurt talk about it, I wish we always had a prevention trial to make that assessment. That would be great. But as Kurt has pointed out, we don't have the trial. The trial would be great, and in treatment, we often have the trials. In most of the cases you're interested in, there is no trial, there will be no trial. So we are going to have to make these judgments, whether you call it suggestive or not, in the absence of the study design we'd like to have. Doesn't mean we can't make a decision, it's just that it's a decision with a different set of parameters.
But when you go back and do this, are you only going to look at the epidemiologic studies?
No, absolutely
Or
not.
you're also going to look at what toxicologists are doing, what clinicians were saying?
Let me make another point about that. And this is sort of a professional issue within the profession of epidemiology. And there's some controversy about this, I'll tell you right off the bat. I do not see myself as a professional epidemiologist as being constrained to examining epidemiological evidence, period. I see my professional role as making decisions about what's best for public health, with other folks as well. Not just me, but I'm one of the voices. And one of the things that I want to do as a professional is to examine the other kinds of evidence that are available to me. It's not just about epidemiology, it's also about the biologic evidence, the toxicological evidence, etc. I won't necessarily make that by myself. Ideally, it would be nice to have a team of people, epidemiologists, toxicologists, different public health people, all looking at this evidence together and making decisions. That's what the IARC does, that's what the Institute of Medicine does, etc. So,
I don't see that suggestion buys you anything except wider boundaries of having people. What is suggestive going to give you that 95% level of certainty does? It's not going to. It's not going to make the situation any better.
Can I comment on that? Because I don't know where this 95% thing came from, other than I can say that within a particular individual study, when there's a study published, then we calculate these statistical significance levels and we say things like, I'm 95% sure that the effect in this study is not due to chance. But when you get to the level of looking at a body of evidence, that issue of whether I'm 95% sure of this body of evidence has now disappeared. It is not a part of our conversation. It is not a part of the methodology. So it's not there. It's only within the context of I'm 95% sure that I can say that chance is not the explanation, but it's not true that therefore I'm 95% sure that causation is the explanation. That is not the same thing. It's not what's actually happening.
That's right. No, I didn't mean that it was.
Dr. Moore?
Yeah, well, just a general comment also. It's useful, it seems to me, to remind ourselves that we are involved in research. And, you know, what that means, it seems to me, certainly with regard to the evolution of evidence, is that truth doesn't come usually from a single study. I mean, we tend, and this is certainly true in the area of clinical trials, we tend to think that, well, because it's a big trial, therefore it's truth. But, you know, it is in that sense, a single replication, a single flip of the coin. And, you know, I think we tend to want answers, and we tend to therefore hang our hat on individual studies, when in fact, the truth, it seems to me, and that's what we're all after, emerges, it sort of percolates through the system in a very slow, not very systematic way.
Yeah, there's another way of saying that, which is that when you have a single study to make a decision from, it is very unlikely from a single study that you'd ever say, now I know it's causal. That would be extraordinary. It's not that it doesn't happen. There are a few extraordinary examples of truly a handful of studies. I think aspirin and rye syndrome might be a good example. The DES and the vaginal cancer may be a good example, but that's the exception. Typically, as I showed you in the alcohol and breast cancer, which then Steve showed you is now a part of the risk factor of one of the risk factors of breast cancer, it's not uncommon to have 60 epidemiologic studies.
Of course, that doesn't help our poor judges very much.
I'm not saying that. I'm not sure I'm here to help you guys.
Well, that just says life is tough.
Yeah.
I mean, it's tough all over.
Yes.
If you've only got one study, then you are more likely to say, I can't make a decision that this is causal based on one study. It would be extraordinarily unusual to do that.
Chuck Barr, so do you suggest then that if studies, like Chuck Barr from San Francisco, do you suggest that if studies haven't been replicated, but there has been a large study about A and B, that we simply point that out to the jury and say, all right, you know, it's one study, and there we are. What do we say? What do we say? Do the judges assume more of a gatekeeping function? Do they say, well, there's only been one study, and so I'm just not going to let that go to the jury? Or do you suggest, look, if it meets all those other criteria, but there's only been one study, let's just tell the jury there's only been one study. And then should we give some cautionary instruction after that?
Well, I think you have really put your finger on a great deal of what we've been talking about for 2 days, which is how does one deal with uncertainty, and that becomes a policy issue, it seems to me. You know, as I said, I teach evidence, and I really do not see these as evidentiary issues from where I sit, ultimately.
Let me just comment on that, because I think, I can't speak for what it is you need to do, but from a scientific perspective, I think it is extremely fair and reasonable to say there's been one study. One of the sort of primary considerations in evidence in science is replicability. That's what the consistency criterion is really all about, in its sort of fundamental sense. Now, when I showed you 60 studies, it's consistent over these 60, but you could imagine that you begin this process somewhere. There was a single study at one point. And we certainly were waiting for that second study. Now, bottom line, we waited for 58 more studies. But certainly you would say, look, there's been one study. We would prefer this study to be replicated for all the reasons that Leon discussed.
But you have to look at it in context. You know, if you're talking about one epidemiology study of DES and a very, very strong biological plausibility and other data, then you're not going to be the judge that says, well, there was only one DES study. On the other hand, you may have 60 alcohol studies, but not that much of a biological model to explain why you shouldn't drink a glass of wine at dinner. So, you know, it's not formulaic. I think that's the bottom line.
I think it's a good point, Jane. There's more than one issue involved in this. We can't just focus on one thing.
And I think we also need to, again, focus on something else Gene said, which is the number of reasons why epidemiological studies won't be done, and that Leon showed us in his little algorithm of why is there no study out there, and what do we do with that?
But with regard to your question, I would certainly pay some attention not only to the number, one study, but something to the quality, so to speak, of that study, because you can say there's only one trial done, the trial involved 20,000 people and 78 clinics, that's a very different one study than a study involving 47 people and carried out in one place. So I think you have to sort of, it's appropriate to count, but you got to count with some value also.
Okay, let's have a few questions from the audience, and then really we have to Liz.
Well, I'm Liz Schneider. I'm a professor here at Brooklyn Law School, and many years ago I worked with Jean on issues of gender and reproductive health. And one of the fascinating things about that work in retrospect was the issue of the subsequent Supreme Court's recognition of the nature of the reproductive hazards in the workplace only after the scientific literature began to focus on the problems of both male and female reproductive hazards in the workplace. Up until that time, the courts had uniformly dealt with those issues from the standpoint of the appropriateness of legal exclusion of women in the workplace because the scientific data had focused on the problems of women's reproductive hazards in the workplace. In fact, on this issue that a number of speakers have spoken about over the last 2 days, I can remember while the case was pending in the Supreme Court, an article January 1st of that year in the New York Times on the front page that focused in on the fact that epidemiological and other scientific studies had now determined that the hazards that men faced were also serious from a reproductive problem. And later that year, the Supreme Court decides that indeed that is a serious problem that is illegal. So my point is to underscore the issues that Jean is raising about the interrelationship between what is focused on and what is studied, the conclusions that that may lead to, not only in the culture, but also in law, and the ways in which a shift frequently in what is studied, and then what gets reported, in a sense, in the culture, in the newspaper, in what people expect, has an impact in terms of then what may happen in terms of conclusions and legal policy as well.
Okay, I think we have time for one more question, Judge.
I'm Keith Allison, I'm from White House, Texas. This is Dr. Minor, and everybody else wants to answer. One thing we've not talked about, for the pressures of time, that is a big part of our docket, is adequacy of warnings. Cigarette packages have long contained warnings. We now see in bars wine contains sulfite. Have there been any tests in terms of the efficacy of warnings? We hear a lot when a drug manufacturer is trying to defend itself that, well, it's all there, we warned you. And in truth, it is generally all there in one of those little handouts. But do we have any empirical data as to how effective any of that is?
Can I just make one short comment that there is a trial of that nature going on right now that's being run by the American Legacy Foundation, which many of you know is kind of the grand master for the tobacco settlement. And it's structured somewhat like the kind of clinical trial that Dr. Minor talked about, but the difficulty of doing something that really is well beyond a clinical control is almost unimaginable.
It's also, what is the meaning of giving a warning to someone who may be addicted? You know, there is some work in the social science literature, and actually, I think at Doug Leach's shop, we've done a number of things on, it's been work on mammography and advice giving.
There's quite a bit of research on positive public health recommendation messages and how effective they are. I'm not aware, but that doesn't mean they don't exist, of studies on the effectiveness of, say, drug warning labels. We could find out for you. I mean, some of the Brian Strom in Philadelphia might be able to better answer that question.
Lawyers in particular.
But I would also say, obviously there's an art form to writing label inserts, and basically you include everything in there that's possible because they're not necessarily designed to inform, they're designed to protect the label. And if you can read the label for people with old eyes, like the fine print and it goes this far, so they're not widely read, but certainly they include everything that's possible because so they're not very informative. And I certainly don't know of any evidence of effectiveness. I'm impressed by the very first study that I was involved in which we produced a result the world didn't want to hear with regard to an oral hypoglycemic agent, and ultimately resulted in a label change to put a warning in a black box. It took 14 years from the time that happened before the warning got put in a black box, and it took the Supreme Court and so on. So what gets into the label is quite political and doesn't help a lot. And if you read the label insert, there isn't a signal drug you would take. Don't read it. I mean, it's because you don't want to know.
I think at this point we're going to end this. We have a lunch available for you on the 10th floor if you want to invite anyone who's at the Marriott. I think we have room to accommodate those people as well. Please take the red books that were supplied by the Federal Judicial Center if you don't have a reference manual. I have a host of people to thank, ranging from our law students who helped in escorting judges, our Dean Siegel, who really was in charge of picking the restaurant, doing all of the work. Most of you also dealt with Michelle, all of our audio-visual people. We're going to do another of these programs November 7th and 8th, and we will send you details about that. We'd ask if the speakers, if possible, would sit at different tables downstairs at lunch, and the same for members of the advisory board. And finally, I have been asked to announce that the dessert in the lunch that you will pick up downstairs is Junior's Cheesecake, which has been voted the #1 dessert in New York by New York Magazine.